Okay, let's take a look at an additional example. So it says a long coaxial cable consists of two thin wall concentric conductor, cylinder with radi A and B. So we can see this is A, this is A, this is B. So this one is the outer cylinder. This is the inner cylinder. So the inner cylinder carry a static current I, and the outer cylinder provide the return path for the current. The current set up a magnetic field between the two cylinders. Calculate the energy stored in the magnetic field for a length of L of the cable. So here we can apply the Mps Law on this. This is the Amperean loop. So we have integration. The line integration of mu BDS equals mu 0 I. So actually this is the I, this is the I. Yeah, so due to the symmetric, we know that this line integral is nothing but B times 2 pi small r. The radius of this Amperean loop is small r, so we have a 2 pi r as the circumference. So equals mu 0 I, so we have nothing but B equals mu 0 I over 2 pi r, which is the most simple, most familiar equation in chapter 29. So next, we can use small ub to be B squared over 2 mu naught, which is the energy per unit volume. So we can substitute this expression into here. So we have mu naught square I square over 8 pi square R square. Just substitute the B here. Well, actually we can also cancel this one, because here we have mu naught, so cancel one of the mu naught. So next, we can write dUB to be UB times the small volume, and actually this is the cylindrical coordinate. So this volume is UB times A dr d theta dz. So actually this part is for the polar coordinate. So this is the z direction, so that it is like in the cylindrical coordinate. So we have dA to be r dr d theta, and then we multiply it by dz, so that this is the area, and then multiplied by the height will be the volume. So so we can just plug in this term into here. So we have dUB to be mu naught I square over 8 pi square R square times R dr d theta dz. And actually one of the R can be cancelled, so we have a mu naught I square over 8 pi square R dr d theta dz. So we have this expression. So next, we want to calculate the total energy stored in this structure. So the total energy UB, will be the integration of dUB, and we can just plug in this expression here. So we have the triple integration of mu naught I square over 8 pi square r d theta dz. And actually we need to determine the lower and upper limit for each of the variable. So for the r, we integrate from small a to b. So we have here from a to b, And for theta, it is a whole 2 radian, so from 0 to 2 pi. And for dz, the length of this structure is small l, so you integrate from 0 to small l. And actually, this expression can be separate for different variables. So we have, or actually we can just put some of the constant in the front. So we have mu naught I square over 8 pi square. All of it are independent to r, theta, and z. So we can just put them in the front. And then we have 1 over r dr, integrate from a to b. And then for d theta, it is like from 0 to 2 pi, or you can regard it as a integration of 0 to 2 pi 1 times d theta, integration of 1, but actually we can just skip it there. And for z, we have similar dz from 0 to l. So this one is nothing but lateral log of b over a. And this one is 2 pi, this one is small l. So finally we have mu 0 I square 2 pi, and this 8 pi square can be partly cancelled. So we have 4 pi at the denominator. And then we still have L, and then lateral log of B over A. So this is the closed form solution for the energy. So for part B, it asks what is the stored energy per unit length of the cable if A, B, I are these values. So rather than calculating UB, we actually need to have UB over L. So we can just simply divide L on both sides. So this L can be cancelled on the right hand side. So actually UB over L is nothing but mu 0 I square over 4 pi times lateral log of B over A. So we can just plug in the value. Mu 0 is 4 pi times 10 to minus 7. So over this 4 pi is 10 to minus 7 times I square is 2.7 quantity square lateral log of 3.5 over 1.2. So this is 7.8 times 10 to minus 7 joule per meter. So actually the SI unit for the energy should be joule, and this is meter. So we have a joule per meter, or you can write it as 78 not 78 micron. 78 should be it should be like 780 nanojoule per meter. Should be like this. Yeah. So here we have an other additional example. So let's see, we have 2 parallel loops of wire have a common axis. So which means that these 2 circles on two different planes which are parallel to each other. And also, if you just connect the center, then this line will be perpendicular to them, to these two planes. Perpendicular to the two planes. So we call it, so this one is called the common axis. Because when you just draw a line perpendicular to the center, then it is the axis, and these two circles share the same axis, so they call the common axis. And the smaller loop is above the larger loop by distance. X is much larger than R. So this distance is X and is much larger than the larger radius. Consequently, the magnetic field due to the counterclockwise current I in the larger loop is nearly uniform throughout the smaller loop, which means as much as we have this approximation, X is much larger than R, we can approximate that the B field generated by this loop over this smaller loop is nearly uniform. It's nearly uniform to simplify the calculation. So suppose that X is increasing, which means X is increasing means this loop may be moving upward, or the other way, or the larger loop moving downward, or they are moving at the same time, but the relative speed is a constant. We have v to be the derivative of the displacement with respect to time. So for part A, find an expression for the magnetic flux through the area of the smaller loop as a function of X. So in chapter 29, we have a 29-24, this formula. When we have a magnetic dipole, then the B field on the z-axis will be this expression. So here we can actually write it as B to be mu naught over 2 pi, which is the same, and mu is actually, this mu is actually the magnetic dipole. If you still remember, mu is actually NIA. Now we have n equals 1, and I is, I here, I. And also the area of the larger circle should be pi r squared for the A. So this mu should be I times pi capital R squared, which is the dipole moment of the larger loop, as much as we have a current on the larger loop. And now it is not z, it is x in this question, so we have x-axis like this, and here we have x cubed rather than z cubed in the denominator, and of course it is on the x-axis, so we have I hat. So this is the B at this point, and as much as we have this approximation, we assume all the B over this area will be a uniform expression. So we can approximate the magnetic flux over the smaller loop to be B times pi small r squared. So it will become mu naught I pi square capital R square small r square over Well, and still we have a 2 pi here and then x cube. So in this case, pi and pi can be cancelled. So we have a mu naught I pi capital R square small r square over 2x cube. Yeah. So yeah. So this is for part A. This is for part A. Yeah, and next, for part B, in the smaller loop, find an expression for the induced EMF and the direction of the induced current. So suppose we know the phi B for the smaller loop, and as much as we have this expression, so you can actually see mu naught is a constant, I is a constant in this example, pi is a constant, R square, capital R square are all constant, 2 are constant. So the only non-constant term is this x cube. This is not a constant because we know that x is increasing. X is increasing. So actually, this term is a varying variable. In this case, phi b is also time varying, which means according to the Faraday's law, we know that the EMF will be minus d phi b dt. So as much as the magnetic flux over this loop is time varying, then there will be an induced EMF. So we can just plug in this expression into here. So we have minus d dt, and then we have a mu naught I pi capital R square small r square over 2x cube, like this. So as much as we know, most of the terms are independent to the time. So we can just put it out. We have mu naught I pi capital R square over R square over capital R square over 2. So all of these are independent to t. So we can just put it out. And the remaining term is d dt. And then 1 over x cube. X is a function of time, so we cannot just put it out. Yeah, so you can imagine this is the chain rule. This is chain rule, so you can imagine it is like f is 1 over x cube, and x is actually a function of time. So we have this one is actually df dt. So it will be like df dx. So f is a function of x, and then according to chain rule, we should multiply it by dx dt. So we have a minus mu naught I pi r square over 2, and then we have a d dt df dx. df dx, x is x 1 over x cubed, which is x to the minus 3rd power. So we should have a minus 3 over x to the 4th power. So we multiply it by minus 3 over x to the 4th power times dx dt is actually v. So we finally have so we have 2 minus sign here, so it becomes positive. So we have 3 mu naught I pi capital R square over R square over 2x to the 4th power times v. Yeah, actually a long expression, but yeah, actually this is the final answer. And yeah, this is the answer for part B, which is the induced EMF. The induced EMF. And next we still need to determine the direction. So as much we can actually determine the direction of the EMF in two ways, and they will be the same. So the first way to determine it is to use the right hand rule. So we have the current to be counterclockwise. So you use the forefinger, follow the direction of the current, and the thumb will pointing the positive x-axis. So forefinger, follow the direction of I, and then forefinger, and then your thumb will point to the positive x-axis. So in this case, this is positive, and as much as we have a positive answer, so the EMF will be the forefinger direction, which is actually counterclockwise. So the EMF and E is a positive. E is positive. So the EMF should be counterclockwise. And the second way is to use the Lenz's law. Lenz's law. So as much as we know phi b, the direction of phi b, and actually we know that excluding the minus I, we know that d phi b dt is a negative number, because that one is a positive number, which means that here we know phi b is defining upward. So this expression corresponds to the magnetic field pointing upward, and this is a positive value, of course, but the first derivative with respect to time is a negative number, which means that the magnetic flux over this loop is decreasing. So according to the Lenz's law, the B induced should be pointing upward to counteract this changing. In this case, the EMF should be counterclockwise, so that it can generate the B induced pointing upward. So actually both of these ways will give the same conclusion.